טוב, אז לי קוראים אמיתי. I'm a software engineer at JFrog. And I work on distributed systems in Go. So that's just about a little bit about my background. I'm studying towards a double major in maths and computer science. I'm almost done. I've been done for quite a while, almost done for quite a while. In my spare time, I'm a computer languages enthusiast. So I'm really into all types of computer languages and what you can do with them and the ideas involved. And I love my bike almost as much as I love software and my girlfriend. That means I love my girlfriend more than my bike. I just want to be clear about that, but I really love my bike. Yeah, so let's go back in time. I want to kind of tell you a story, a little bit of history. So the year is 1978, and the programmer is Tony Hoare. Tony Hoare is a Turing Prize recipient, Turing Award recipient. He invented the quicksort algorithm at age 22. And he also invented the null pointer, which he later called his billion-dollar mistake. So he's, done some good things, done some bad things. Pretty respectable guy in general. And the problem that he's trying to solve in 1978 is that it's becoming apparent that parallel programming is going to be the future of software development. And parallel programming is hard. So he realizes that concurrent software is the future of performance software. That's the way the world's heading, even in 1978. Processes running on many processors, running in parallel, schedulers, etc. And he wants to define a single way to write concurrent programs, which isn't available to him at the moment. What they had then is quite similar to what we have now, which is mutexes, semaphores, condition variables, all kinds of elements to allow us to program concurrently, but there was no like one true way to program concurrently. Maybe similar to how we would program sequentially, where everyone understands loops, if-else statements. There wasn't these kind of paradigm constructs for concurrent programming. Yeah, I think it was Biggie Smalls who said "Mo mutexes, mo problems" in his 1994 album "Ready to Die." So yeah, so Hoare was searching for a solution which would provide him with 3 attributes. The first was simplicity. This is pretty self-explanatory. He wanted any programmer to be able to look at the concurrent software he was writing and to reason about it easily, to talk about it with other programmers as he would any software. He wanted the solution to be abstract, meaning that software developers wouldn't have to think about concurrency while they were writing concurrent programs. So they could just think about the ideas that they wanted to convey in their software, and the implementation of the concurrency would happen behind the scenes. And finally, and this is probably the most important, he wanted his solution to be composable, meaning that he could scale up his concurrent solution, add more concurrency, and that it would still be viable. It would continue to be simple and abstract. So what he came up with is something called CSP. Has anyone here heard of CSP, by the way? Okay, that's cool. 3 people. So this was huge in 1978. Hoare published a paper where he describes a new programming language. And even though it's technically a programming language, I want us to think of it in this talk more of like a philosophy, as a way of thinking about concurrent programming. And technically, actually, it's an algebra, but that's not important. If anyone's interested, I'll link the paper at the end. And he calls this language, algebra, philosophy thing, he calls it communicating sequential processes. So his language has primitives of process input and process output, and it has a structure of parallel composition of sequential processes. So this is probably gibberish to most people, so let's dive into this. In short, his idea is to have small, independent, and sequential software units. All of the software units run in parallel to each other, and they communicate with each other using message passing, otherwise known as channels. So does this sound familiar to anyone? Is anyone, sorry? Sorry? Erlang. Erlang's actually really interesting. I was hoping someone would say Go routines, but that's actually, it is the case, but what I was thinking of is shell commands. So how is this similar to shell commands? Let's take a look. So consider the following command. Can everyone see this, by the way? Okay. So we're doing a cat on a foo.txt file and then grepping for the word bar and then t into a file called baz.txt. So this basically means we'll read from foo, we'll filter out all the lines that don't have the word bar, and then we'll write the output into a file called baz. So what's happening here actually? So cat, grep, and t are all small sequential processes, right? They're all communicating with each other over channels, which in this case is the pipe. So cat is communicating to grep over a pipe, and they're executing concurrently. That's something that we don't think about a lot while we're using the terminal, that when we compose commands in this way, cat, grep, and t are all set off at the same time, and what synchronizes between them is actually the pipe. So they're all running concurrently. So what a crazy concurrency model. I think this is absolutely amazing. Like, none of us ever think of concurrency while we're using the terminal, right? We just think of writing commands and the concurrency happens behind the scenes. So basically what we have here is a concurrency model, which is simple because what's written here is really understandable. It's abstract because, as I said, no one ever thinks of parallelism while they're writing commands in the terminal. And it's composable because if we want to add more functionality or we want to change the command, all we need to do is like we did here, where we throw in a sed command. We just need to change our commands a little bit and we'll get completely different functionality. So this is kind of the essence of CSP. This is the idea that Tony Hoare was trying to give across. And this is the kind of ideas that we want to program with when we're programming in a kind of CSP style. So yeah, we have here like writing sequential code, which is boring, and then writing parallel code, which is okay, and then writing sequential code and running in parallel in the shell, which is amazing. So, yeah, so back to CSP. I want to compare CSP a little bit to Go and how the syntaxes match, just so we can see the similarities. So in CSP and Go, we can read and write from channels. In Go, the way we would read from a channel is using the arrow operator. So here we read card image from card reader. In CSP, it's very similar. We use the question mark operator. So here we read card image from card reader in CSP. And we can write to channels, of course, as well. In Go also arrow operator to write line image to the channel line printer. In CSP, we use the exclamation mark. So very similar in general. And an important point is that in CSP and in Go, channels are blocking until there is a reader or a writer on the other side. So if I write to a channel in CSP, I have to wait until someone reads from the channel before I can continue operation. And this means that channels are more than just a tool for passing information, they're also a tool for synchronizing between different threads or between different processes. And we'll see how this comes into play a little bit later on. So executing sequential code is something which every programming language can do. You can do it in Go. Here we read from a channel in, increment a variable I, and then do some conditional logic. And you have exactly the same kind of functionality in CSP. And we can also execute concurrent processes, of course. No concurrency model would be complete without this. So in Go, we just prefix a function with the Go command in order to execute things concurrently. So here, disassemble, squash, and assemble will all run concurrently. And in CSP, we can do this using a double pipe operator. So to run disassemble, squash, and assemble together, we can just put them together with this double pipe operator. So another important point about CSP is that in CSP, processes never share state. Any shared information in CSP has to be passed over channels. And what this gives us absolutely for free is an absence of data races. So because we have to copy any information between two channels, only one process can ever see any copy of data, and we can never have data races in CSP. Cool. So the final thing I want to talk about is the select command. I won't go into what select command can do because it's not so important if you're not really aware, if you're not a Go programmer, but it's a really powerful tool for selecting over events with channels. We can do it in Go using this, this syntax. So here, if X is larger than Y, we'll perform some logic. And if we can read a variable C from the channel in, we'll do another logic. And in CSP, you actually have exactly the same behavior. You can achieve it with this # operator. So here on the left, we have the case of X is larger than Y. And on the right, we have the case where we read C from the channel in. And this is really interesting because all of these features, blocking channels, simple parallel functions, the select case syntax that we have in Go, these are like the jewels on the crown of Go's concurrency model. These are things, we think of these as modern, sleek design implementations of Go, when in fact, they were thought of by Tony Hoare more than 50 years ago. So, or almost 50 years ago. So that's interesting. That raises eyebrows for me. So CSP is also a very rich language, regardless. I won't go into all of the syntax. It's not really important. But if anyone's interested, yeah, I recommend it. So in practice, because CSP is so simple and the model is so simple, we can actually develop tools, or tools have been developed to prove the correctness of CSP code. This means that we can prove absence of deadlocks, we can prove, or there are obviously absence of data races, and we can prove the correctness of CSP code. And these techniques were used to write safe concurrent code for the International Space Station in the 80s. So really powerful language, really powerful ideas. And a number of languages emerged that were directly inspired by CSP. One of them is Occam, very niche language. And another one is Newsqueak, which is also incredibly niche, but it's really interesting because Newsqueak was designed at Bell Labs by Luca Cardelli and a guy called Rob Pike. And if any of you are unaware, Rob Pike is one of the designers of Go, one of the 3 designers of Go, and probably the most influential person in the design of the Go language. So all this just goes to say that the similarities that we just saw between CSP and between Go are no accident. Rob Pike was fully aware of CSP and the powers of the CSP thinking when he implemented channels and when the Go concurrency model was created. So I want to see how we can apply like CSP thinking into the way we write Go, so that we can really utilize the full power of the Go concurrency model. Cool. So the example I'm going to give is something called the sieve of Eratosthenes. Does anyone know what this is by any chance? I've got the one mathematician in the room. So the sieve of Eratosthenes is an algorithm for finding prime numbers. And the reason I chose it, and don't read this, this is just an example, but the reason I chose it is because Hoare gives this exact example in his original paper in 1978 for how we can use CSP to write concurrent code. So I thought it would be a nice little example, kind of link us back to history, for us to do it here together. So the sieve of Eratosthenes, the problem statement is as follows. Given a large n, how can we find all the prime numbers up to n? So in this case, we have n equal 25, and we want to find all the prime numbers up to 25. So the first thing we do is we remove 1, because 1 isn't prime. And that's a fact, and don't argue with me. And then the second thing we do is we take 2. 2 is the first prime number, and we can mark it with an asterisk. We know it's a prime number. And more than that, we know that any multiple of 2 isn't prime. So we can remove all of the multiples of 2, so 4, 6, 8, all the even numbers. We can throw them out. They're definitely not prime. Next, we move on to the next number, 3. We mark it, it's prime. And now we can remove all the multiples of 3. So 12 goes, 9 will go, 15 will go. Any odd number, which is a multiple of 3, is now also removed. And we continue in this manner. Now we move to 5. We remove any multiples of 5, etc., etc. Eventually, we're left with all the prime numbers. Okay. So fairly simple, but we'll see how we can do this concurrently using CSP, which is not so simple, maybe. So first of all, how would we write this sequentially, just simply in Go? So What I have here is just a very straightforward sequential function, which does exactly what I just described to you. We first make an array of all the numbers between 0 and n, or which will represent all the numbers between 0 and n. We can set 0 and 1 to be not prime because 1 is not prime. I said that already. And then we can just iterate over all the numbers. If the number is prime, we can set all the multiples to be not prime. And finally, just print all the prime numbers. It's pretty straightforward. And here we have a pretty decent implementation of this algorithm. It's not optimal, but we can optimize it. And we can get to a complexity of n times log n. Not very important, but we can do that if we want. But you're sitting at your day job in Ancient Greek Algorithms Incorporated, and your boss comes along and he tells you, that's great, but can we make this parallel, please? You know, I have 10 processors, I want to use them. So how would we go about doing this? So we have, I'll just go back to the code. We have this shared data structure here. And this array. So we might have to put a lock on this array so that if a lot of threads wanted to access it concurrently, we would have safe concurrent access, but we're going to take a different approach. We're going to think like a shell, exactly like I said before. We're going to compose the ideas together exactly like a shell command. So I want you to imagine the following command. Just imagine, this isn't what we have yet, but imagine that we're going in this direction. So sec to 100 is going to print all the numbers between 2 and 100. So 2, 3, 4, 5, 6, etc. up until 100. And then the first sieve command that we have here will filter out all of the even numbers. So it'll print 2 and filter out 4, 6, 8, etc. And then the next sieve will filter out all the multiples of 3, just like we did in step 2. And then the next sieve will filter out all the multiples of 5, etc., and then we'll be left with the prime numbers. So I'll just go through that again, so we're all on the same page. So sec outputs a list of numbers from 2 to 100. Sieve is a command which is going to take as an input a list of numbers. It's going to print the first number out, and then it will pass on all the numbers that aren't a multiple of the first number. Okay, so as an example, the first sieve will take in the numbers 2, 3, 4, 5, 6 up to 100, and then it will first print 2, the first number, and then it will output any number which isn't a multiple of 2. So it will output 3, 5, 7, 9. The second sieve is going to print 3, the first number, and then it's going to output all the numbers which it got, which aren't a multiple of 3. So 5, 7, it skips 9, and then we go on to 11, and we keep going in this way. And we're going to chain a lot of these sieve functions together, and eventually we're going to get all the prime numbers in this way. Cool. So there's 3 things we have to do here. 3 fairly simple things, and we're done. The first, we need to implement the sec. The second, we need to implement sieve, and then we need to tie them all together, and then we're finished. So sec is fairly simple. It writes the numbers 2, 3, 4 to a channel out until canceled. So it receives a channel done so that we can cancel it at the end, and it receives a channel out to write to. We defer closing the out channel. We'll get to why that's important at the end. And then all we do in a loop forever is we just write numbers 2, 3, 4, 5, 6 to the out channel until someone cancels us. And when someone cancels us, we just return. So that's sec. The sieve function receives an in channel, a list of numbers coming in, and has a list of numbers going out. We again defer closing the out channel. We'll get to that at the end. We print the first number, and then we can just go over all the numbers that we get in. If the number is a multiple of p, we can skip it, and otherwise we can pass the number on to the next sieve. Cool. So that's the sieve function. How do we compose all of this together? So the idea is as follows. Cool. So we're going to start off with our sec function. It's going to pass off the numbers 2, 3, 4, 5 to the first sieve function. The sieve function is going to write to an out channel, which is going to be the in channel to the next sieve function, which will be the out channel to the final sieve function, to the next sieve function, and so on until we finish. And then I just want you to notice that each sieve, this sieve will print the first prime number, this sieve will print the second prime number, this sieve will print the third prime number. And then once we get here, we know that we've printed all the prime numbers we wanted to print. So once this sieve starts passing on numbers, we know we're done. So we can just take that output, put it straight into the sec, tell it we're done. The sec will close. This will close the next sieve. This will close, and we'll exit gracefully. Okay. So this is the last piece of code where we're completely done. So how does this look when we chain it all together? The first thing we do is we start our sec function. We give it a done channel so that we'll be able to tell it to close. And we give it an in channel so that it can write to the first sieve. And we set it off in a Go routine. And next, 100 times, we set off a sieve function. And every time we set off a sieve function, we tell them the next in channel will be your out channel. So the in function for the next sieve is the out channel for the previous one. And then finally, we can just take the last out channel and pipe it directly into the done function to tell the sec that we're done, and this will print all the prime numbers for us. Okay. So I just want to show you this working because, you know, I want you to believe me that this actually works. And then once we've done that, we'll be done. We'll have created our first CSP style concurrency. So let's take a look. So this is the code. This is all of the code. It may have seemed a little long while I was talking about it, but this is actually the full implementation of this prime number generator. And let's run it. So go run sieve. Ta-ta, we get the first 100 prime numbers. If anyone wants to check this, the code is on GitHub. Yeah, so that's it. So what have we achieved here? We ditched the shared data structure. We ditched the array that we had before. And instead we favored streams of data, which we could more easily reason about and pass between our different functions. So this is the core of the CSP idea. We also achieved all of this with 0 locks. It was all done using channels, which in my opinion are much easier to reason about as a human programmer. And we created composable concurrency that scales naturally. If we want to add more or we want to generate more prime numbers, all we need to do is generate more Go routines and we'll have more prime numbers for free. And the final bonus thing is that actually this implementation, without even thinking about it, gives us optimal complexity for this problem. So we did it in O of n log log n. Again, exercise for the reader why this is O n log log n, but believe me, it is. So that's it. Thank you very much. And does anyone have any questions? That's true. For every prime number, you need a Go routine. So I just want to say this idea, the idea is cool. Never write this for a prime number iterator. It's much slower than doing it just with an array. This was more to show the idea. But in Go routines are really, really cheap. So there are a few kilobytes of memory and they don't actually open an operating system thread. So you can run thousands, tens of thousands, I think up to millions even, and it will, you won't see any kind of performance issues with that. So you can get 1 million prime numbers quite easily with this implementation. Yeah.
Is there an actual
Yes, very much. So my original talk, I wanted to start with this and then go on into all the ways that I use this in my code, but that would have been an hour and a half. But I think that the idea is, first of all, you need to get used to writing code that looks like this and not like classical concurrency code. So it takes a little bit of learning, just like in the same way you learn how to use a mutex and at the start it's really unintuitive and then you learn how to use it. I think it's the same with this kind of code. And I think what I said about preferring streams over data structures is the heart of it. So if you can, especially with things like arrays and arrays of arrays, usually you can move those things into streams of data which move between functions rather than a single instance which everyone has to talk with. And it makes your code a lot easier to understand, in my opinion.
My question was like, a tip for what would be a natural implementation of such code. Say, hey, everybody should you just said you shouldn't be using that. You're doing just integration. So what is a good implementation?
Okay, that's a great question. I think with I/O, it's definitely the big one. So things like caches, where maybe you need to get something from a cache, but it takes a while because the cache has to perform some kind of network operation or disk operation, and you have to wait for this. That's a really good place to move your data into maybe a stream rather than a cache, which holds it in a data structure with a lock. Another thing would be handling requests, for instance. So handling network requests, moving things through streams of data rather than having an object which holds, I don't know, your requests or whatever. Those are the kind of things I would say. Anything else? Yeah. Yeah, so the way it works is that if we'll just do two, let's say cat and then grep. So what happens is the operating system starts the two programs together, and it just tells the grep read from the pipe, and every time you can read, start working. So the cat will start up. It will read a line from the file, and then it will pass it to the pipe. And then the pipe will then output a line to the grep, and grep will be able to read one line and output to the terminal. And then the cat will read another line, and then grep can read another line. And this way they both actually work together rather than having to read the whole file and then to filter through the whole file. That's the way it happens concurrently. Anything else? If there's any technical questions about the code, if someone didn't understand something, I'd really be happy to go over it. So feel free. Sure. By the way, all of this is on my GitHub. I'll make sure to put the GitHub up at the end. And the original paper that I took this from is also on my GitHub for anyone who wants it. לא, זה הכי טוב שיש, כאילו, מה שכתבנו פה. בפועל זה הרבה יותר איטי, כי יש הרבה overhead של המערכת הפעלה או של ה-Go runtime, של לנהל את ה-Go routines, אבל סיבוכיות תיאורטית זה הכי טוב שיש.